Okay, so let's consider a traffic model. We'll suppose that traffic is traveling down the x-axis in the positive x direction, and that the car density is given by rho at location x and time t, and that's expressed in terms of cars per kilometer. We'll take v to be the local car speed at location x in kilometers per hour, and then rho times v will be the flux in cars per hour. Okay, so what we're going to do now is we're going to set up an ODE for the density rho. Okay, so to do that, we notice that people drive more slowly when density is high. Okay, so really velocity is going to be some kind of function of density, and we need to figure out what that looks like. So let's say that rho sub m is maximum density. And by maximum density, I mean that traffic is completely jammed, so motionless, once the density equals rho max. Okay, and so jammed, that means that velocity should be equal to 0, right? Okay, so suppose that velocity is proportional to the remaining space on the road. So in other words, is proportional to the difference between the current density and the maximum density. Well, then that means velocity is proportional to the difference between max density and current density, just like in the setup for the logistic population equation. Okay, well, then this is this one we can rewrite by pulling out the rho max as c rho max times 1 minus rho over rho max. Okay, so now maximum velocity, let's call it Vm. This is going to occur when density is 0, right? So the maximum velocity is going to be c times rho max. And this means that our velocity is max velocity times 1 minus rho over rho max. Okay, with all that underway, we can now see that flux is going to be given by rho times v, which according to the formula we just worked out is rho times v max 1 minus rho over rho max. And so the corresponding conservation equation is going to be time derivative of rho plus space derivative of flux, 0. Okay, so if we rescale a bit by saying let's take u to be the renormalized density, so just as a pure fraction, so a number between 0 and 1, then this conservation equation is going to become ut plus Vmax times the space derivative of u 1 minus u And if we work out what that derivative is, so multiply out the quantity inside the parentheses, and you have a u minus u squared, so that becomes a 1 minus 2u. Then this is ut plus vmax 1 minus 2u times ux by chain rule is equal to 0. So the upshot is that this is a nonlinear advection and the speed is just going to be the coefficient right here of the ux part. So that's Vm 1 minus 2u. So this is the speed of a traffic wave. So this is like speed of, say, a traffic jam. So if you have a spot in the traffic flow where it's really dense and suddenly slow moving, then what happens is the cars are going to drive into that clot at the back end, and it's going to take them a while to get through the dense spot. And meanwhile, the cars that have already made it through are going to be on the leading edge of that clump, and they're going to suddenly speed away. And so the dense part is going to move slowly backward, opposite in the direction of traffic. And the lovely thing is that you can actually see this, because if you look at the speed that this thing is moving at, this thing is going to be, well, without working it out, it's just negative. And this is exactly what you see in traffic. So if you are approaching an interchange and there's a traffic jam at the interchange, that traffic jam is going to move backward down the flow of traffic away from that interchange.